All right. Good morning, good afternoon, and good evening to everyone across the world. We'll go ahead and get started. We're the Iceberg team, we were really looking to harmonize SAR imagery and laser altimetry. So here we'll start off with an example slide. On the left, we have Sentinel-1 looking at some of the physical ice conditions. On the right, we have a Sentinel image detecting ships. So if you're perhaps a ship captain who's embarking on a journey close to ice and want to know what those ice conditions might be, well, the issue is if you're using Sentinel and you look at the ice that you look top down on is very different than the ice that you would be looking straight forward. And so perhaps knowing some more of the physical conditions of that ice, that would be something that you might be interested in. So namely, we were looking at extracting that information using ICESat-2 and taking height profiles of icebergs. So in general, this process, we divided into 4 tasks. And on the right here, I've included some of the major members who did those tasks. So the first is, okay, if you want to compare these data sources, you need to know when those instruments are going to overlap with each other. I think that actually this was the hardest part, and certainly in the future, automating it is also, something that might be even more difficult. So the second is obviously we want to combine different sets of data together. So we have, the ICESat-2 and SAR data acquisition, right? Mainly so that we can, calculate the iceberg height to extract some of that physical understanding. So the third, we want to look at, ships using SAR. And the fourth is combining all this together and giving some context to the other tasks, tracking and mapping icebergs based on the available observations. So this is mainly using GIS. So the first part to start, we decided to really focus on specific icebergs, to find candidate icebergs in potential overlap locations, and then to go from there. So it's a lot of data engineering, a lot of restructuring in a GIS. And so using this type of information alone would be incomplete because, right, these observed sightings, they're just these point locations. They don't come with any physical details. You don't know the extent, you don't know what it looks like. It's just a single point on a map. Another thing is that the data only really tells you where significant icebergs were and when they pass those locations. So certainly filling in the gaps using Sentinel and ICESat-2, this could be very useful. So this is a slide, I think, Lampros, I don't know if you're on, if maybe you want to explain more of the process of extracting the iceberg extent. Okay, so in basis, right, the idea is that very easy to calculate the extent, the area of ice, but that's not the whole picture when navigating these big icebergs, right? If we have this, right, we can calculate, oh, this iceberg is 191 square meters, but if that iceberg is 5 meters tall versus 40 meters, very different in terms of planning to navigate those. So I think this is Isolde's slide. I will pass it off to her.
Thanks. Okay, so this is a different iceberg, a very famous one that broke off of the Larsen Sea ice shelf a few years ago and almost collided with South Georgia. And for this specific iceberg, we knew it had an intersect with ICESat-2 because it was used in another study. So we use this to try writing a code that measures the iceberg height. So if you can go to the next slide. So this is the track that intersects with the iceberg. And as you can see, there's a gap in the data for sea ice height and for ocean surface height for the ATL07 and ATL12 products, which means there's also going to be a gap in the sea ice freeboard product, ATL10. So we can't use those products to measure the iceberg height. But if you go to the next slide, we can see the iceberg in ATL03. So where the black line goes up a little bit, that's where the iceberg is. So I've made a bit of a quick and dirty code that kind of measures the iceberg height, not very exactly, but it works, I think. So if you can go to the next slide. So you can see those red dots a bit vaguely. That's every 150 photons grouped to the mean to find the surface. And the next slide. So we applied the mean sea surface height, ocean tides, and inverted barometer effects. Those are all geophysical corrections that were available in the ATL07 product. So we applied those to get to a kind of fake ATL07 product where the iceberg is available. So here we can see that this specific iceberg goes to around 38 meters, which I think is correct for this one. Yeah, if you go to the next slide. Here you can see the actual ATL07 product. So it's not always, yeah, it doesn't work perfect yet, the code. There's a lot of improvements that can be made. Grouping into 150 photons is not the best way of finding the surface, obviously, but it was a quick way to get there. Yeah, next slide.
So I think a lot of this was Lampros. So I'll begin explaining Lampros. If at any time you want to chime in, please do so. So the biggest. Oh.
Can you hear me? I'm sorry, I had again a problem with my microphone. What we did is we just used the database of the icebergs, and we just wanted to find intersection with the ICESat-2 data and with the available Sentinel-1 imagery. So first we began with the Sentinel-1. We found the intersection with the database of the icebergs, and then we moved to the ICESat-3 photon data. This image is actually close to the iceberg, but it's not a perfect match. It shows the Atlas 07 photons. And the image on the right, it shows actually it's probably the Isolde's image. It shows in the upper of the image the height of the iceberg. That's all for this slide, I guess. The next slide is probably Isolde's or not?
I think it's Eric, if you're on.
Mm-hmm. Yeah, so in support of this work and future work, we thought it would be easier to try and find overlaps between ICESat-2 data and Sentinel-1 data. So we built off of the slide rule tool and the slide rule tutorial, where in this new tool, you can draw a bounding box, and slide rule will return the overlapping tracks. And then from those tracks from the bounding box, we look for the spatial intersection with Sentinel-1 footprints. And based on that, we find the shortest temporal offset between those two intersections. So for example, you can see in this middle plot here, on the y-axis, you have the relative ground tracks throughout time. And the color represents the time offset between the ICESat-2 track and the closest Sentinel-1 track. So from this plot, we can also get the closest Sentinel-1 granule. So given any specific ICESat-2 track, we have Sentinel-1Zs that intersect with the specific granule to make analysis easier in the future. And I think I'll pass it back off to the last slide.
So yeah, this is kind of a quick summary of everything we did. Right, a lot of the ICESat products, very easy to use. If you're looking at sea ice in large concentrations, right? Obviously, icebergs, kind of even just finding them in any source is much like finding like needles in a haystack. So. Right, it was nice that we could use the ATL03 raw measurements and bypass, the limitations of the other products. So in the future, right, a lot of this should be automated and really, finding an iceberg, just knowing where it is physically, and then being able to get the height. That would be, I think, a large benefit for a lot of different types of people. Another issue is finding smaller icebergs, little pieces of ice. Not a lot of those features are reported simply because there's so many of them. So in the future, right, applying machine learning, being able to differentiate those pixels, that would include some huge improvements. And so at the end, maybe we can create an online dashboard, an online tool for like maritime ship captains. So with the small remaining time I have, I want to show you all just a little dashboard that we made that summarizes this all up. So this is live right now. I'll make sure to include a link for those of you curious. So we just have a lot of these layers. We have, for instance, our ICESat-2 height profile. Well, looking at the height profile, we don't really know, some of the other spatial characteristics that come down later down the line. So we can add some context layers. So we can overlay an iceberg track. In this case, this was the iceberg A68A. So from the height profile, we can look and we can, scroll and zoom through, this map and see, where this ends up. So this is I think right here is South Georgia Island. So a lot of cruise ships go by there because it's a remote location. So, right, we also have, right, but just by looking at the line, we don't know, kind of the progression and the history of how the iceberg has traveled. So we've included point locations where you can assess, updates in the location as well as, the spatial coordinates. And so the last bit, we try to include some of the Sentinel imagery. So these are web tile layers. Unfortunately, the framework that we're running this in doesn't support large-scale web tiling layers. But, if we were to implement this into an enterprise system, maybe use, some REST API, that's certainly something that we could release to the public. So that's basically everything we have. I'll go ahead and end there.